I'm going to talk about the Seismo-ionospheric precursor observed by FOMOSAT-7, and this is I sent you the wrong file. This, okay. Anyway, I think we can proceed that one and can save some time. We actually using the two satellite dissect FOMOSAT-5. To do that one. So I'm going to show you FOMOSAT-7. Allow me to say something. It's actually for our study, we actually can answer the question about the so-called the spatial precursor. So let's move on the next slide. So the FOMOSAT-7 actually will be observed, the worldwide by using the IVM, that's meaning ion density drift velocity, together with this so-called the radial occultation. And whatever we observe over here is the blue dots stand for the radial occultation, and the gray line stand for the IVM. The IVM actually measure the electron density, and ion density and ion temperature, and also ion velocity. And I'm going to use as one of the Indonesia earthquake to demonstrate whatever we do over here. In fact, we also have a FOMOSAT-5 because I sent you the wrong file, and FOMOSAT-5 the slices won't be able to see over here. But I think the spirit will be the same. First of all, I would like to answer the one or two questions. Regarding the so-called the three element by using satellite, and also with this GPS TEC, we will be able to observe worldwide, the ionosphere. So based on the previous earthquake for particular area, we will be able to tell you when the earthquake is coming. So that's mean time. And the other one is based on the anomaly, we will be able to see how what's the magnitude, for the possible forthcoming earthquake. And the third part is where is it? So I'm going to show you by using the GPS TEC and also available the so-called GIM TEC, we will be able to see the location. And finally, we will also show by using satellite observation, not only see the ion density or the plasma density together with the electric field. I think everybody love it. That's meaning we can see the physical causal mechanism of the so-called the Seismo-ionospheric precursor. Okay, follow next slide. So this is a typical data. You will be able to see it. It look like the satellite image. You can see the global ionosphere all the time. And if we can, for example, for this event, we can monitor the location like in Indonesia, like this, the one with this, the red star symbol, and the other one with a red rectangular one, and that will give us the chances to see how that responds to the so-called equatorial ionization anomaly, and then we will be able to estimate the electric field. Next slide, please. Next. Okay. Overshoot. Back a little bit. Okay. I think this is the earthquake. You can see that one. This was November 2019. And that's a location that's in Indonesia, Bitung. And the right panel, and you can see the SIP, and that's meaning the top panel is for F10.7, that's the solar radiation. Second one is the KP index, that's a magnetic index. The third one is the DST, that's a stone index. So we will be able to tell if there's a stone, and also or any other space weather. So as we can tell over here, the 7.1 earthquake that's occurred on the 17th of November. And so we can see without any reason, in the bottom panel, you can see 19 days or 20 days before the earthquake, you can see the then actually you can see that those is the curve. Actually, that's it's like the monitored right above the area. The red curve stands for the observation. The black curve stands for the so-called upper bound and lower bound. And here, this is based on the so-called mean-based, construction. So, whenever the observation exceeded, 15 days, before the earthquake, and at the same time point, if that exceeded, the upper bound and lower bound, we can detect that one, consider that part is a so-called anomaly. So the marker with a red dash, in SIP that stand for the so-called the possible Seismo-ionospheric precursor, and you can see the red curve, the shade. That's meaning the strength is deviated from the median value. So whatever the anomaly is not based on what I'm saying, it's actually based on the the satellite observation data. And also, I will draw your attention. And you look at the middle panel, which is LLT plot. That means stand for EIA crust. That's meaning before the earthquake, without any other reason, the EIA crust actually become strong and also move toward the equator pole. So the vertical the circle latitude, that's when you move this south pole and north pole. That's meaning the electric field the eastward electric field has been intense during the the SIP period. That's meaning October 25th and 26th. Okay, move on to the next slide. Hello. Next slide. Okay, yes, thank you. So if we overlap, the so-called anomaly, we count by that. Actually, the globally we will be 5183 lattice. That's meaning we observe globally simultaneously, and we will see how that the anomaly occur. During the 19 days or 20 days before the earthquake. As you can tell, that one. The mark that which is so-called the red, and with specifically inside that's a rectangular. That's a 0.4% of the whole total growth of the group. That's meaning, this anomaly doesn't appear everywhere. Actually, it's specific over the right above the epicenter. So I will show you the following that one, which is a FOMOSAT-7, how that occur. And I will draw your attention. Actually look at this is a 28 letters, the time period, time point actually is almost 96.4%. This is specifically over there. That's meaning no other places. Okay, move next one. Next slide.
Yes.
We'll move.
Oh.
Got hunk.
Sorry. Nothing is wrong.
Okay, good. Yeah. So okay, let's look at the the also satellite orbit. You can see actually this is covered by the FOMOSAT-7, which is IVM. I think that this is Komogawa is going to be you guys are going to like it because we recently develop a new satellite payload that can put on the CubeSat, so-called the CIP. That's the advance of unfortunately I didn't show you the FOMOSAT-5. That's AIP. And so that will measure the ion density, ion temperature, ion velocity. So here the IVM is a early version of our AIP. As you can tell, that one on the left top side, that's an observation of the on the October 25th. And on right, the middle central panel, the top, that's the one. This is observation of the 10 of October 26th, and the central panel for the left and the middle, that's a stand for the 1 to 30 days before the the 25th and 26th, and from bottom panel from the left and the center, that's meaning the observation subtracted their reference. So you can see that one right above the the epicenter, that's also become very red, and that's meaning the ion density also increase. If you compare the previous slides, that's meaning during the the 19 days or 20 days before the earthquake, globally, specifically over epicenter, the TEC increase. Now ion, plasma density increase. And I magnify the one on the very right, the panel top. That's meaning that 20 days before the earthquake, over the epicenter, you can see the density or the ion density specifically increase. 19 days before, also the same thing. Okay, so this is not randomly. So if we can, the spot and detect the anomaly, that's meaning we can see the earthquake before they are coming. Okay, next one. So actually, I just showed you the EIA crust on the October 25th, 26th, the move to the equator wall. Okay, that's electric field. So if we can use this satellite data, this is a GIM data. If I use the satellite, the simultaneous measure that one, if we can see the electric field over that one, it's also eastward. And this is a physics. Okay, this is not a bad guessing. Next one. And we using the ground-based GPS, and we recently developed one of a program, so-called the GIS. So we can see the globally the three-dimension, electron density change. So by using radial occultation, and you can see the top panel that's 20 on the 24th of the observation date. That's meaning if you calculate it by the during that period, and the bottom one is the difference between the observation day and also the 30 days before. So you can see the density increase over there. And then next slide. And if we purview the side view data, you can see the density increase a little bit on the UT09 and UT10 and the 11 UT. Next one. For the 25th, okay, now, and again, the top panel is the observation. Second, the lower panel is the difference between the 25th and the reference. Next one. Now it's more clear, and you can see the red one. So actually, the density increase. How that shape, that means we see the anomaly in the purview, the latitude, longitude. Now we see the purview from the three-dimensional cut. Next one. And if we go back next, okay, this 26. So you can see that's even more clear. Next one. Again, 3 dimensions. So you can see how that the change, right above the, the epicenter. One. Okay, next one. And next one. So it's a lot of, so you can see all the detail. And if we move on that one, and I'm sorry, I sent you wrong slides. Actually, if we use IVM data, okay, I think we can see that one. Let's move on. Go. This is a lot of data. Okay, here. Now, this is the radial occultation. We select the sum of data file, and the red curve stands for observation, and the blue and the dash, black, that stand for the reference. So on the 25th and 26th, you can see that one, the density increase above the F2 peak, and the raise up, if the electron density raise up, that's meaning the eastward electric field, and with the northward, the magnetic field. So you get a E cross B. So you push up all the ionosphere profile. Next one.
Tiger Sensei, can you wrap up in 3
Okay,
minutes?
sure. Okay, I will finish that in 2 minutes. Okay, on the left panel, and you can see that's ion density. The box on that's an increase. That's meaning the observation. The gray level one, gray color one, the box that stands for the so-called reference. So on the center one, that's again is ion density is increased. The bottom panel is the other UT time. The central bottom, that's also increased. So in situ measurement and the remote sensing total electron, they are well agreed. Okay, this is science. And on very right, and you can see the top panel, and we calculated with this E cross B, with this dynamo approach. We can estimate the electric field actually is 0.64 millivolt per meter. Again, on the bottom one is the 0.34, the millivolt per meter. Okay, move on next one. So I will give it a remark. So the GMTC and the FOMOSAT-7 Cosmic 2 radial occultation electron, the NMF2 significantly increase, or the electron density significantly increases over the epicenter. Actually this is which is suggested, the 14th of November 2019 magnitude 7.1 Indonesia earthquake has been detected. And the FOMOSAT, radial occultation electron density profile, the motion suggests the eastward electric field. has been enhanced. Okay, and that's agree with the EIA crust motion. And Seismo generated it, the electric field. For the Indonesia earthquake, actually it's about 0.34 to 0.64 millivolt per meter than the eastward. I think this number is very, very reasonable. Okay, I think I'm going to finish this one. Thank you for your attention. Yeah.